You know, one of the best ideas in energy engineering in decades is fundamentally doomed. I'm talking about those small nuclear power plants, aka small modular reactors. And these SMRs fix every technical criticism of nuclear power. But they can't solve the problem that matters most. And that's fragility. The SMR might be the most elegant piece of engineering this century. Factory-built modules, passive cooling, standardized design. But I think it's the wrong direction. Not because it's stupid, not because I dislike nuclear. I used to work in nuclear. But because the real problem with nuclear power was never engineering precision. We were so damn precise, it's unbelievable. It was fragility, and fragility doesn't disappear just because you shrink the machine. Let me explain what I mean. A fragile system is one that suffers disproportionately when something unexpected happens. A robust system resists shocks, and a resilient system absorbs shocks and recovers. What matters isn't how a system performs under normal conditions, but how it behaves under volatility. And the world is bloody volatile. So the real engineering question isn't, is this efficient? Is it clever? Is it theoretically safe? The question is, what happens when something does go wrong? Traditional nuclear power plants were designed to be extremely safe. And statistically, they are. But they're also tightly coupled, high-energy, centralized systems. And tightly coupled systems don't fail gracefully. When something breaks, the consequences are not local. They propagate. We've seen the pattern before. 1979, 3 Mile Island. US nuclear construction froze for 30 years. And then there was Fukushima, Japan, 2011. Germany immediately shut down 8 reactors and Japan mothballed 54. 54 reactors. Each event had disproportionate political consequences. That's the fragility I'm talking about. Different countries, different reactor designs, and different political systems. Entire national energy strategies changed overnight. That's fragility. A disproportionate consequence. There's also the financial fragility. Nuclear requires 10 to 15 years of capital commitment before an ampere escapes its steam turbines. Solar and wind, on the other hand, just 6 to 18 months. In volatile markets, that's not just a risk, it's guaranteed exposure. Now, SMRs generally improve an older design. As their name implies, they're smaller. They rely on passive cooling. They're built in factories rather than chaotic construction sites. Companies like X Energy are developing designs where each fuel particle is individually encapsulated, reducing meltdown risk even further. This is bloody serious engineering. If your constraint is construction delays or active cooling failures, SMRs are a strong answer. But they don't change the deeper problem. They don't change the system's exposure to political or financial shocks. They don't change its symbolic sensitivity. And they don't change the fact that nuclear operates under a demand for perfection. This creates a vicious circle. Demand, perfection, extreme regulation, higher costs, fewer deployments, less learning, and higher costs again. Whereas solar and wind tolerate failure, rapid iteration, cost curves dropped 90% in 10 years. Massive deployment, more learning, lower costs again. One system fights its own economics, the other accelerates them. Solar and wind energy systems are anti-fragile, meaning they actually improve when they fail. The engineers learn, and 18 months, 2 years later, improvements are on the market. Nuclear's learning rate is negative, it's fragile. Each plant is more expensive than the last. Solar and wind, consistent 10 to 20% cost reduction per doubling of employment. That's not an engineering failure. It's a system property. Fragile systems can't iterate. Anti-fragile systems thrive on iteration. Honey, we shrunk the core, but we didn't shrink the regulatory interface. You still have to produce 100,000 pages of documentation for 300 megawatts. That's the same as you would produce for 1,000 megawatts. The administrative load per megawatt actually increased. Think about the world we actually live in. The SMR is a perfect local optimum. It solves the reactor problem flawlessly. But engineering is played at global levels here, where the constraints aren't physics, they're economics, time to market, and public trust. Imagine a cyber attack takes down 10% of Texas wind turbines. Who cares? What happens? An energy price spike temporarily. Repair crews fix them, no evacuation, no international summit, no regulatory freeze. And now imagine the same attack on a nuclear facility near Washington, D.C. or New York. Even with no radiation release, the markets will panic. One system tolerates failure and improves, and the other amplifies it, and the response to failure is amplified too. What happens? Deployment freezes. Nuclear isn't just physically sensitive, it's politically and financially sensitive. This isn't about whether nuclear is statistically safe. Per terawatt hour, it may be safer than coal or gas. That's not the argument. The argument is about the consequence topology. Solar and wind distribute generation across thousands of millions of units. They decentralize risk. They tolerate failure. They don't require 40 years of perfect governance to function. They don't depend on uninterrupted public confidence. And they don't collapse politically because of a single event. You can install solar in a war zone. See Ukraine. You can't deploy nuclear without a functioning state. That's resilience. SMRs tried to make nuclear smaller, but the real vulnerability was never size. It was consequence. You can shrink the core. You can improve the cooling. You can standardize the manufacturing. But you can't shrink the political reaction to a nuclear incident. And in a volatile world, political reactions matter. The small modular reactor is brilliant engineering inside the box of nuclear power, and that's the problem. The box itself is fragile. Solar and wind, by contrast, changed the architecture entirely. They lowered energy density per unit. They distributed generation. They made failure boring, and boring systems survive. This isn't an anti-nuclear rant. SMRs are clever. They're technically impressive. They may even operate safely for decades. But when I look at energy through the lens of fragility versus resilience, I don't ask, is this safe enough? I ask, does this system tolerate being wrong? And nuclear, even small nuclear, still demands a level of institutional perfection that history suggests is unrealistic. The future of energy won't belong to the most elegant machine. It will belong to the system that survives its own mistakes.